Hello, this is Rachel. I'm going to ask the moderator here, is it okay to start, or are you going to introduce me? Oh, spectacular, great. All righty, hello and welcome. My name is Rachel Pedreschi, and I am going to be talking about hot, some like it hot. I am actually filling in for Gian Merlino, who is the PMC chair for Apache Druid. And so this is actually his talk, and I'm sure I'm not going to do it justice the way that he can, but we are going to talk about some pretty interesting things. First, the data temperature spectrum. So what that means. We're also going to do on a little tour, find out how this temperature spectrum, how it's changed through the years, and how it went from earlier from cold to hot. So we're going to go on a tour of through the years, see how things have evolved, have they scaled. We're going to meet Apache Druid, and to see how it fits in the space. And then we're going to ask ourselves, can we have it all? And the thing that we're always wondering is, there one system that does it all? And of course, the answer is, well, maybe. Anyway, is an introduction to myself. My name is Rachel. I run the community program here at Imply. So we support Apache Druid in the wild. So my job is to tell everybody about Apache Druid, explain where it fits, when to use it, and to support everybody in their journey in this particular space. My experience goes back 20 years, back to the wonderful world of the first database built for data warehousing called Redbrick back in the 90s. And I've also worked for, along the way, companies that range in the cold and hot spectrum of analytics, from Business Objects and Jaspersoft, Vertica, DataStax with Cassandra, and now I am finally 3 years here at Imply, working with Druid. So what are some of the things that we care about? And so at the top, we have this beautiful bowl of hot Cheetos and Takis that represent hot data. And on the bottom, we have a warehouse, which I think has some government cheese. It's even in black and white, and that's representing cold data. For hot data at the top, we're thinking query speeds that are sub-seconds or just a few seconds. We're generally going to be working with data, so it might be true real time or near real time, but it's data that's been loaded within the past few hours. And in generally, we care about fresh stuff, and we're going to have high concurrencies. So these hot data sets, the part of the reason they're hot is because they're so critical to the business that we want to put them in front of the largest number of people, not just professional data people, but like end users, like product managers, marketers, that sort of thing. And the use cases are going to be really highly interactive. So people are going to be spending a lot of time inside these tools. They're not just going to be reporting and leaving. They're actually going to be doing a lot of investigation. And I'm going to use the term OLAP, or online analytical processing, to describe that throughout the rest of this presentation. So on the other side of the spectrum, we have our extreme government cheese, our cold data. But in this world, slow queries are okay. We might not care how slow they are. They might be reports that get generated overnight, for example. We might be okay with minutes or even hours. Less fresh data is okay, because we're going to be doing a lot more reporting and a lot less operational stuff. Generally going to be lower concurrencies, and we're not going to have as many people using this. It might just be our professional data people. So the use case for hot is around reporting and planning. The use case for cold is around reporting and planning less than being highly interactive. So for example, this is a tool that we make at Imply, as you might have guessed, as Imply is the Apache Jury project. We're all about hot data and fast stuff. So this is a tool that we made called Imply Pivot. And it's making a tool like this work properly, which is actually what inspired Druid in the first place. We wanted to build something that was able to power this kind of interactive experience, even at scale, even at a massive amounts of data. And this was done at a company called MetaMarkets. I think Druid is about 10 years old now. And they they looked at all the systems that were out there at the time to support these types of interactive applications. And they looked at search systems, and they liked the idea of a search system because it had real-time data and it had a flexible schema, but it wasn't really good for analytics. So they looked at analytic systems like OLAP systems like Vertica, and those were great for doing OLAP and ad hoc queries, and they could scale pretty well, and they were pretty fast, but they didn't really do real-time data. Their Kafka ingester at the time didn't exist, but even now it's still even kind of in a micro batch fashion. The last type of system that they looked at was were like the traditional time series databases, because the types of queries they were going to be doing, because they were machine generated and generated a lot of data, were going to be very time series oriented. And what they found is a lot of those were back-ended by key value stores, and the key value stores weren't just were not going to scale to the types of amount of data that they needed. So anyway, so why did this matter? You know, what do people do? Why is this ability important? So we might call this real-time OLAP, and the two use cases that fit into it most likely are exploration and monitoring. And exploration, meaning I want to drill into my data, I want to do iterative questions, I want to understand what's happening. Then monitoring, meaning that I want to know what's happening right now, observability. These two things come together for these real-time OLAP workflows. So that being said, so where does it matter? Well, these hotspots, if you want to say it, are useful in a variety of applications. So some of the ones that we've seen people adopted are for the stuff on the slide. So risk and fraud analysis, useful because they need to deep dive into things to figure out what's going on. Data-driven applications is a really big one. That's a case where concurrency is going to be very high. You might have a large number of people outside your organization accessing a data-driven application. Network performance is another one that's going to be very operational in nature. The real-time, fresh aspect of things tends to be very important there. Clickstreams is a similar situation. Freshness matters for understanding rollouts of new products, doing A/B testing, but even the ability to do a lot of exploration over historical data is very good. When trying to find trends and figure out what your users are doing and how their behavior, digital advertising is the market that everybody loves to hate. Although it did bring one nice thing to the world. It was a genesis, of course, and inspiration for Apache Druid. So that it's in a space where even the smallest players, even the smallest advertising customers generate a truly tremendous amount of data. So the need for tools that are scalable and efficient is that so we can at least thank them that data warehousing situation where you might have a data warehouse that you're looking to expose to more people, you're looking to make it more real time, you're looking to get more applications built on top of it. So if you're looking for a platform to make that happen in a performant and available way, metrics. If you're if you're sort of into time series metric store applications, there's also a lot of overlap with the time series world and analytical world, and they're coming into this collision over time. So, and then there's IoT, which we've come up a lot as well, where the number of devices can be truly incredible. So these are all variety of situations where the scale and concurrency number of users, you want to get in front of amount of exploration that needs to happen, the amount of observability that needs to happen, meaning that you want to treat them as much as hot. So, but then why tolerate cold data? So that demands the question. So why do we tolerate it at all? So why not make everything hot? And of course, the reason is cache. And I don't mean in-memory cache, I mean actual cold, hard money. The reason is that making large amounts of the data available at hot speeds is something that costs a lot of money. It requires memory, it requires hardware, it requires network bandwidth, and then the business case to spend that kind of money might not be there for everything. So let's take a little stroll down memory lane and look at the architectures of these systems and how some of these systems evolve to become hotter as some systems evolve, well, to be colder. So we're going to first go get into our Wayback Machine. And we're going to go way, way, way back in time. Okay, that might be a little bit far back, but you probably get what I mean. And so this starts at the beginning. It started with a single relational database, one size fits all. And this is the world that I joined the industry in. Everybody had Oracle, and you're using it to store, well, not at the time shopping carts, but now shopping carts, or you're storing your products in there because you're trying to sell on an e-commerce website. And that works great. And you're doing your analytics and your production database because you don't have that many customers, or, you know, way back in the 90s was because you didn't know of it. There wasn't any other options. But the thing is that you don't really have much data. So let's go forward a little bit to the 90s. Al Gore created the internet. So thank you, Al, for that. And we have more data. So at some point, the single OLTP database stopped scaling well. So the next thing you're going to do is build a data warehouse. You're going to have your relational database that's only going to be used for OLTP style data, online transaction processing, and it's going to be used to power the actual application or the actual business case that you're offering. You're going to develop some sort of ETL, extract, transform, and load process. So, and I apologize for all the acronyms, but this is in my world, it's rife with acronyms. With all those acronyms, you're going to load your data warehouse, and your data warehouse is going to enable you to do the same kind of analytical queries you're going to do on your single database. But by offloading it, you are minimizing the production impact of doing these type of analytical queries. And you're potentially getting the ability to do these analytical queries in a more scalable way. But one of the issues with the old school data warehouses is, you know, you have a tough time scaling them too. And you put a lot of data into them, and they would get slower and slower and colder as you added more data. The ETL process would almost take 18 to 24 months, according to Gartner at the time. Eventually, that would be too slow to make any real use for them. And they basically become ice. And so in order to warm them up a little bit, you would add something called an OLAP database on top of it. And this would create a subset of the data. Some people might call it a data mart, or it would become a cube like in Cognos or in Business Objects. It might be a summarized version. It might just be a few tables. It might be coarser granularity. You might only have daily aggregates instead of having the raw data. But you know, you do something to it to make it more manageable, to put it in an OLAP database. So now it's hot again. So you've taken your ice cold data and you've made it hot. And you have the situation where this architecture was very, very popular. You have a data warehouse where you have all sort of your data cold, but in there, your OLAP database or OLAP cubes, you have some type of summarized, maybe it's not for full fidelity, but it's available hot. So let's go forward a little bit more in time to the 2010s or so. St. Job of Apple had bestowed upon us the great mobile applications. We have the big data world. So now we have a lot more data. And everything is starting to scale in your single relation database. Nobody's doing that anymore. Now everyone has a sharded relational databases. Instead of putting all your shopping carts and your products into a database, you're going to split them up by customer. Instead of having a data warehouse, you're going to have a data lake. And your data lake is going to be either a Hadoop-based data lake using HDFS, or it's going to be a cloud data lake using S3 or something like that. It's pure storage, getting data from the thing that runs your business to the thing you're going to store it in, and you're going to have some type of ETL process again, or ELT process. It could be change data capture. It could be Kafka. It could be that you can use, for example, Kafka Connect to capture change logs from your relational database and dump them into data, and then dump them into Kafka, and then get them from Kafka to a data lake. There's lots of ways to do this, but one way or the other, you're getting it in there. And then you've scaled out a query engine to the scale. The query engine enables you to do the same type of analytical queries you could do from your old data warehouse. But now you can do it from the data lake. And everything is scalable there. The sharding allows you to scale out transactional database to your heart content. The ETL processes are all scalable as well. The data lake, of course, is scalable storage. And then the query engine to add processing. So everything's scalable. It's beautiful, but it has a downside. It's slow. Scalability. We've got scalability, but we've slowed everything down. And now we're in the world where we're using query engines like Hive or Presto, and we know they work, but these queries on large amount of data are just taking a long time. So something that people start doing, again, in the kind of the mid 2010s, just a few years ago, is storing optimized copy of the data in a serving database. People might call this a Lambda architecture. But one of the things that got really popular for that was Cassandra or HBase. And the serving databases are going to store an optimized copy. This is starting to sound a little familiar. It probably sounds like the pre-big data world with OLAP databases. The serving databases are going to store some kind of optimized copy of your data designed for hot access. And a lot of the ways that people did this, like I mentioned in the early days with key value stores like HBase and like Cassandra. But this is where Druid comes in, because HBase and Cassandra were not designed for true analytics. They were designed to provide hot data, but now we're adding a lot of complexity to the system. So let's go to the now. And we now have a service expectations. I'm not going to be pointing out Gen Z here, but they grew up with these iPads and these iPhones in their hands, and they expect their data applications to run in real time. I even have an obligatory Gartner quote here that not only are we going to have people who demand access to faster, quicker, fresher data, but there's going to be a lot more of them. So more people, like I mentioned earlier, are going to want access to data, not just your data people. So this is where Druid comes in. What we've done is try to build the best serving layer that we could possibly think of. And that means a few things. That means we're targeting very high concurrency, we're targeting very low latency queries. But we're also targeting a lot of flexibility in the kind of queries you can do. So one important thing about Druid, which we'll get into a very few slides, is that it's not actually a key value store. It's based on an underlying column-oriented data store. It's the same kind of columnar storage that you would see in a data warehouse or something like an org file or a Parquet file. But on top of that, we've added indexes. We've added the ability for streaming ingestion. We've added the ability to do batch loads from data lakes. And we've added a whole suite of resource management features that are designed to give you the kinds of performance that you're looking for, even under highly concurrent workloads. And what that means is that in your data architecture, Druid is going to fit in like this hot analytics area of the stack. You may still be using a query engine for your colder data, and your warm data query engine like Presto. A little bread, by the way, is my representation of warm data, and but also like a cloud data warehouse. And you'll be using Druid for things that have these hot requirements. One interesting thing there, of course, is why we don't use to retrieve everything. Why don't we use a query engine for everything? Why does it make sense to have both? And we'll talk a little bit in later slides, as well as start to explore this idea of why we can't have it all. So where are we getting with all this? And where are we getting is Druid. So I'm getting a little ahead of myself. So the reason that people use things like Druid is because they're looking to power analytical applications. And it's especially interesting to use a technology like this for analytical applications, because if you have any of the problems of scale, of high concurrency, of streaming ingestion, of wanting to provide people with a lot of observability, but it also has ability to do ad hoc exploration, it's really important to have a system that scales well and that performs well, that's able to power that stuff. So people will put a lot of applications over the years. On the left, of course, you have one that we built called Imply Pivot. On the other, there's applications that have official support added for Druid. Looker, Metabase, Superset, SQL, of course, which is not an application, but you can query with it. And if you're using query, that you can make your own custom applications. We see a lot of customers and a lot of people using custom, JavaScript and React type of applications that use Druid as the back end. So Druid is used pretty extensively in the wild, and the project's been around for a few years, like I mentioned earlier. And a lot of the earlier and biggest adopters were tech companies here in the Silicon Valley. And of course, the reason is that these tech companies were just some of the first to have these big data problems and have these big data scale problems, and some of the first to adopt technology designed to solve it. So, for example, Netflix for real-time insights on experience, or they use MoPub, which is a Twitter subsidiary, for querying terabytes of data in seconds. And they use to power analytics at Airbnb as well. What all these use cases have in common is that they're huge, and they're performing very, very well. So ingesting 100+ billion rows per day, retaining trillions of rows per year of retention, hundreds of servers, query latency is still sub-seconds to a few seconds, and it makes for both streaming and batch ingestion. So we do a lot of internal benchmarks, of course, but like I like to say, there's lies, damn lies, and benchmarks. So you should really only trust benchmarks that are done by third parties. And this is some data that a benchmark done by an academic database research group, showing the performance of Druid on similar data sets versus Hive and Presto, some SQL query engines. And you can see a pretty massive difference here, 20 to 59% over times over Presto, 100+x over Hive. So what's going on here? Why does this happen? Druid, as I said earlier, uses a column format. Hive and Presto can read columnar formats as well. Druid is integrated with the data lake Hive and Presto. So what I want to say is that Druid is faster than Presto and Hive, and we're going to talk about some of the reasons why, but that doesn't necessarily mean it's better. It's just used for different use cases. And I am going to plug, if you are watching this in real time, a meetup that we're going to be hosting with Netflix, that we're doing with the Trino folks. So I should probably be saying Trino versus Presto here. Sorry about that. And they're going to be talking about how they're using both Trino and Druid to create a overall data warehousing architecture that includes, cold, medium, and hot levels of data. So follow me on Twitter, and you'll hear all about when that's going to be. Anyway, so how does all this work? So to figure this out, we're going to pop the hood and ask ourselves what's going on in there. All right, so internally, Druid uses a microservice kind of architecture where we have a bunch of different processes responsible for a bunch of different things. And I don't want to go into a ton of details of how all these works because I don't want to bore you to death, but there's plenty of documentation out there, and there's some really great videos. Specifically, check out some ones by Peter Marshall. But suffice to say, you get a full explanation in the docs. The part that I do want to touch on are these little boxes everywhere, these little columnar yellow boxes everywhere. And these boxes are stored in deep storage, and they're pushed there by the indexers, and they're pulled out by the historical. These are processes in Druid responsible for reading and writing data. And when those little boxes are, we call them segments, data segments, and each are a few million rows, and essentially a micro partition of the data set. So when a really big data set is going to have thousands or tens of thousands or even millions of these segments, and they give us is each segment is individually compressed and indexed. And the parallelization system that Druid has built out by fanning out queries to all segments involved in the thing that they're trying to do. So what happens inside them is really where the magic is. You can call it Druid magic. So we built this fan out system just to fan out queries to thousands of segments per query. And then within each segment, we're trying to process those 5 million rows as rapidly as possible. And that's the key to the performance. So I'm going to talk a little bit about a sample query and how it operates on the scale of a single segment. And then imagine that happening 1,000 times in parallel to give you the answer you need. And to do that, I want to talk about how the engine and data format are integrated. So there's a few things I'll talk about. One is compression. In Druid, we have a columnar format. Every column is individually compressed based on that type, and secondary indexes. This is one area where we start to differ from a lot of other query engines do. A lot of these core engines have great data lakes, don't have secondary indexes, but it turns out to be very powerful. Operating directly on uncompressed data is also really important. Some of them do it to varying degrees. And late materialization is also critically important. This is a fancy database person term for saying, don't read it, you'll have to read it, which is going to be a really common theme, as we'll see. So this is the layout of a Druid segment. A typical Druid segment is going to have a few million rows in it. This segment has 8 because that's how many fit on this slide. The segment has 5 columns. So in Druid, we stored data oriented by column. The first column here is time, and you can see it's a long type 64-bit integer. The second column is artist. So imagine this table of ticket sales in various cities or various musical acts. So we've got AC/DC, we've got Perth and Sydney. The artist column is a string, and then there's 3 components to it. The data component, where there's 1 entry per row, and it's just an integer. And so these are the first 3 are zeros, the second 2 are ones, and the next is 222. And what this is saying is, it's a dictionary encoded string values. So the first 3 rows being 0, 0, 0 mean that the first 3 rows of this particular data sets have artist AC/DC, and every first 3 rows, and then the next 2 are both Kylie, and 3 after our Silverchair, we do this. Excuse me. So this is a form of compression. It makes the data segment smaller, especially when there's a number of unique values is low relative to the number of rows in the segment, which is common for a lot of columns. It's not university, but it's common enough. This is quite helpful. But this doesn't perform compression. It also enables it to operate on the compressed data. So you'll see it a bit. When we do a group by artist or group by city, we're actually using these numeric keys to do the grouping rather than the strings, because we can process numbers faster than strings on a computer. The next section is a dictionary. The dictionary tells us what each dictionary code means. And then the third one is the index. The index helps us filter. So what the index is saying, there's going to be a single entry in the index for each entry in the dictionary, and they're corresponding 1-to-1. It's a list of rows that contain a particular dictionary value. So the first section of the indexes, which the rows have AC/DC and so on, are compressed using an algorithm called roaring bitmaps. We also operate on them in their correct compressed form. So if you want to do a comparison, we're actually going to compile compressed roaring bitmaps together, do another round of mmap. And finally, the last 2 columns, we'll skip city. The last 2 columns, price and counter, are both numeric columns, just like the timestamp columns, and so they're stored the same way. All right, let's do an example query. So here's a sample query. We want to look at all the sales for AC/DC. We want to break it down by city, group by city, and then we're going to get a total price for each city. Really straightforward. This is the type of query that's actually the type of query you're going to do in Druid, because you're going to do some type of filtering, some kind of grouping and breaking down, and there's going to be some type of aggregation. These are the kind of queries that are going to power these interactive analytic experience we're trying to power, and you want to be very flexible with the type of queries we can do. So you want to be able to support any kind of filter, any kind of grouping, any kind of aggregation. So because of that, we're not going to want to pre-cache anything. We want to just focus on computing whatever gives us as quickly as possible. So the first thing we're going to do is resolve a filter, and we're going to do that in the dictionary. AC/DC is, the dictionary is stored in order, so we don't actually have to read the whole dictionary. We can just do a binary search through it to find the correct value, which is what we do, and we see the AC/DC is 0. The next thing we're going to do is retrieve the index for that value. So that's going to be the first row in the index section, because it's the first row in the dictionary section. Now we're going to see that we get a compressed bitmap that reps 0, 1, and 2, and the first 3 bits being set representing the first 3 rows containing that value. So now we know which rows contain that value. And this is actually super important. This is one of the first ways that we start different from what standard query engines today that are like what we do. A lot of them don't do secondary indexes, because that is the way you need to, because the way you need to use secondary indexes is it involves a lot of random access. And that requires data actually being stored on the server. And we'll discuss this more in a bit. But Druid is actually prefetching all this data before the query happens. So it has the data stored locally, typically on SSDs. Definitely want some type of attached storage with however much cache memory you can. It doesn't need to have all the memory, but we typically mix memory and SSD because we're able to use these indexes. So okay, anyway, we use these indexes and we know that rows 1 and 2, and the first 3 rows qualify for the filter that we're looking for. The next thing we're going to do is the variation. So we're going to group by city and select price. And so the way we do it now is we go to the data section of the city column. you can see that we have not gone to the dictionary, the index, there's no need. We just need to know what the first 3 dictionary values are. And it's 2, 1, and 2. So the first 2 prices are 1800, 2912, and 1953. So we're going to build a little array, and we're going to use that array to aggregate these things. And the reason we're doing that is as an array, because there's not that many cities, there are only 3. So what we're going to do is we'll build a 3-element array, and then anything we see for one of the cities will go into an element of that array. If there was if there was a lot of cities, more than we can allocate for array, then we would use a hash table. So we choose a hash table array based on how many things we anticipate grouping. And anyway, that being said, we chose an array because there's not that many cities, and it's only going to have 3 elements. What we don't know ahead of time is what cities we're going to say, but we know there's only 3, and so we're only going to see stuff for Perth and Sydney, and only those 2 are filled in Melbourne has an all store net. And at the end of that, we don't have to read the rest of the data section for the city column, because we know from the index for artists that the only first 3 rows contain anything we care about. We don't need to read the dictionary yet, because we don't really actually care what city values are. So yeah, we're just aggregating. The next thing we're going to do is we've done an aggregation, and now we read the dictionary to see what the actual values are. And we do this after aggregating, because typically when we're doing a group by, a lot of times the output of that group by, the number of group rows, is much smaller than the number of rows you're reading. So it pays to defer this dictionary lookup into later. So this is the idea of operating on compressed data as long as possible. Anyway, at this point, we know that Perth and Sydney are the 2 cities, number 1 and 2, of the tickets that we're looking for. And so we can, at this point, we're done with the query on this segment. So let's look at what we've done. We've done a binary search throughout the dictionary section of one of the columns. We haven't looked at the entire dictionary, even though we've just looked at pieces of it. We've done a single random access to the index section of that column. We have read just the sections of the city and price columns that we need based on the index of the artist column. We haven't read past the first 3 rows because we didn't need to. And we've only read the first 2 values out of the dictionary using random access for the city column. So we've really been very economical about how much data that we've read from disk from memory, and how much we've had to transfer to the CPU, all that stuff. So this is where we get our performance from. We get performance from being extraordinarily economical about how much data to read and process. And then once we process each segment in an economical way from every segment, we have built a partial result, and then we're just going to have to merge them together. This process in a well-running, smoothly humming Druid cluster, even on top of billions and billions of rows, is going to happen in less than a second. So, can we have it all? So let's look at some of the differences between them. With Druid, we're doing batch ingestion and streaming ingestion. We're actually ingesting things because Druid is not just a query engine. It's a database. It stores a copy of the data. When you read data, especially ahead of time, partitioned in an index, and this ahead of time fetching the index and well participating in balancing of the data, all contribute to performance that is beyond what a simple query engine on top of a data lake is capable. But it does have one advantage, and that's going to be able to fetch data on command. And fetching data on demand means a couple of nice things. It means you don't have to ingest it at first. If you have some data in some goofy format to create in Druid, you have to go through an ingestion process. Something like Presto can query directly, or Trina can query directly. It's not going to be very fast to do in each individual query, but it may be quicker to get off the ground in the first place because we want to load the table first. This ability to fetch on demand also means that the elasticity can respond much more quickly. So Druid is an elastic system designed for the cloud, and you can scale it up and down. It's as easy as adding more processes, and it's scaling down as easy as terminating them. And the system will self-balance and self-heal in response to this. So Druid is a totally elastic thing. But when we need to fetch data ahead of time, we basically have to balance the data before a new server can be used. When you add a new Druid server, the server doesn't participate in queries for generally a few minutes to an hour or so. And what that means is that if you're elastically scaling it up, it will scale it up and you'll be able to use that new capacity. But it will take a few minutes for it to become available. Whereas a simple query engine doesn't have any locally stored data. You can imagine spinning it up by doing both a query and then torching it down. So the elasticity can respond a bit quicker with that type of system. Yes, both, of course, have elasticity. They're both fault tolerant. They're both shared nothing in the sense that the servers don't coordinate with each other. And they're both scalable to a very large degree. So there it seems that they have a lot in common. And these differences, a lot comes down whether or not we fetch some data ahead of time or we're indexing ahead of time or not. The use case for Druid is that you're going to get better performance on the same hardware, that prefetching of the data, the indexing, the increasing efficiency. So the price performance ratio is really great. And what you're also going to get a lower performance floor. And what I mean by that is that you'll be able to do it to get queries that are sub 1 second, even sub few hundred milliseconds. Whereas with a query engine on top of data lake, it's going to be really tough to get their query latencies that low. But the core engines are nice, and you can have a lot of federated data sources in there. You can query things that were not previously ingested into that query engine, and you get spot elasticity. You get the ability to elastically scale up and down very, very rapidly. So can we have it all? That's the question I thought I want to leave you with, is that these use cases are very different. The architectures are really not that different. We have relatively minor differences, like are we prefetching the data or not? Are we collecting the data on demand? Are we able to query the data in something rather than our native format? Are we building secondary indexes or not? Are we intelligently balancing or not? One reason that I really like working with Druid is that because I think it is a good platform for exploring these ideas. And I think it's a good platform for eventually building out a system that you're going to be able to have, that eventually will let you have it all. And we might not have that today, but it's a world I'm really excited about working towards. So the last question before we go to questions is, how do you get involved? If this piqued your interest or you want to learn more, tons of ways of getting involved. Of course, the easiest were an Apache project and available on GitHub. So come check us out. This was actually screenshotted from today. So come join us, come join the conversation. We do, Imply hosts a druidforum.org, which is a discourse-based site to have new and experienced users get up to speed with Druid as quickly as possible. You can also download directly from druid.apache.org, or you can use the Imply version from imply.o to get started. But again, follow the project on Twitter. Come listen to our talk with Netflix on actually how to build a system that has it all, that has the hot data from Druid and the colder and warmer data coming out of Trino. So thank you all. I guess it's time for questions. Okay. I'm gonna stop sharing for now. How do you guys compare with ClickHouse? That's an excellent question, and it's a question that I get a lot. So at a high level, ClickHouse and Druid are solve similar use cases. For sure. And then there's another one called Pinot. So to be fair, there's 3 of them that are really architecturally very, very similar, meaning that they all sort of answer the same type of workloads. If I was going to put, but they all have pluses and minuses in terms of their architecture and what they do well and what they do less well, I would say. So in terms of ClickHouse, and again, I'm not an expert on it by any stretch of the imagination, but from what I've seen and what I've worked with is that ClickHouse's joins are a lot further along than Druid's. We still recommend with Druid to only use joins for very specific use cases. So if you need a more join functionality and there's no way for you to do that upstream, then ClickHouse might be something good to look at. But from Druid's streaming ingestion is exactly what semantics that it has with Kafka. From what I've heard, is a bit more advanced than ClickHouse. So if that streaming portion is important to you, then Druid might be a better option there. It also tends to be easier to scale. So ClickHouse is really easy to get going on your laptop and get working with. But again, from people who I've spoken to who've used both systems, they say that ClickHouse is just more difficult at scale to get up and running. Updates. I saw somebody ask about updates, and actually Pinot is, if you have a heavy update use case, Pinot is probably the right place to look. Druid Druid writes segments that are they're immutable. And so if you do need to do updates, we can update data that just require, it will create new segments, and those segments might be smaller or not, or out of order from the rest of the data, and we'll have to run a compaction process in order to make those segments better. So if you have a few late coming updates, or you have to update data that is, once in a while, or at a very kind of known interval of time, like all of your updates are going to come in within a day or so, it makes it very easy to schedule compaction to fix that. If you have kind of updates that are happening all the time and there's no way of really knowing when or how, probably Druid isn't the right choice. Right. Do I have any other questions? Oh, can it do 1 petabyte per cluster node before compression? It's all, so the way that we size Druid clusters is, you're going to be CPU. Okay, anyway, so let's start. A Druid cluster has 3 major node types. There's a data node that runs historical processes and middle managers. And middle managers are the ingestion and the real-time ingestion process. So your data nodes are your workhorses, and those are going to be where you're going to be storing your data. There is also a concept of deep storage, but the deep storage is not queryable. It's just there for backups. So I assume, Sergio, that you're asking about live data, 1 petabyte per cluster. As long as that you have the disk space, and the disk space is fast enough, and the CPUs be able to operate on that data, then I don't see why a petabyte of data per node would be not available. It's just, that's just going to be an extremely expensive in terms of having enough SSD storage there. I mean, you can use SATA drives or some of the hard drives, but you're going to be losing some of the advantages that you get with Druid because you're just going to be waiting for I/O the whole time. We do find that customers who are running an Amazon using EBS seems to really cause latency issues, rather than using sort of like the i3 line that has the direct attached storage. All right, next thing. For a time series data, should we use Druid or InfluxDB? It depends on your use case. Both of them can support time series data. It depends on what you're trying to do with that time series data and how much data you're going to store. As I said, and again, last time I looked, Influx is based on a key value store, and key value stores are not traditionally great at table scans. They're great at scanning the data that you're looking for, while Druid was really, really designed for table scans. So if you think about your use case in that way, are you going to be having to table scan tons and tons of data, and you might be aggregating that data, and you want to provide true ad hoc analytic capabilities on top of that? Druid's probably the right choice. If you are going to be trying to store a bunch of time series data, and you're going to be only looking at very specific times that are more suited to a key value sort of lookups, then Influx is probably a better choice. So no, Sergio, there isn't any size limits for the cluster. I was just talking to a customer in the Slack channel. So there is a Slack channel that's hosted by ASF, and they say they have a 1.5 petabyte cluster. And I forgot how much data they had per node, but it was definitely more than 300 terabytes. So yeah, that definitely those scale and those size of Druid clusters don't scare us. That's perfectly fine. Any other questions? Yeah, I apologize. Trino is the new Presto. I'm sorry, Rob. That was definitely my bad. I work a lot with the Trino guys, and I felt terrible about. I realized what I was doing after I said it, so I'm sorry. So do you see limits in reaching 100 to 1,000 petabytes? Wow, that's a lot of data. Now I don't, but let's go for it. And if you guys want to do it, we'll get some of the committers to help you through it, because that would be a pretty epic cluster. Every test that we've done is that Druid is linear scalable. We don't see a drop off of performance at any point, but something that size, yeah, let's chat. Yes, again, assuming the hardware is available. And that's one of the reasons that we haven't tested it, because, well, we don't have that much hardware lying around. Let's see if I've had any other questions behind. Well, you're very welcome. I'm glad you found it informative. Spectacular. Please, feel free to reach out. I'm going to put my email address here, because I don't think I put my email address actually in the talk. You can also follow me on Twitter, Rachel Pedreschi, or check out Druid. Come to the Slack channel. Come to Druid forum. Tell them that you saw me here. And I got swag I can give out. Since we don't do in-person events, we are mailing it out. So if you have any interest in swag, be sure to hit me up. So I guess, Tom, do you want me to stay on and answer any questions that might come along? Okay, cool. I will definitely stay here and hang out for a little while. If anybody has any other questions, please feel free to hit me up. Thank you, everybody, for coming today. Normal latencies to expect for point queries when the data size is in the range of 100K to 1 megabyte. Again, data size, meaning are you scanning that much data, and what type of queries are you doing? I would say generally you can get, if you have the right hardware, you're going to be able to get most of your queries done under a second with Druid. That's the goal. Join queries, we definitely push that out a little bit. Right now, joins and lookups are still kind of held in JVM memory, so that is a limiting factor. But if we say if you're going to be doing like a big join, is probably more like a couple of seconds. But on a fully denormalized or a flattened table, then you should be able to get under a second with the right level of hardware. And if you want to hit me up, I can walk you through a sizing exercise. I have a really cool little sizing spreadsheet that helps you see the differences and trade-offs. Like, so if you add this much more RAM, you can get this much better performance, or if your SLAs are half a second versus 2 seconds, how much concurrency that you can work on. I'm trying to get some time to make this into a publicly facing document, but has not happened yet. All right, well, I am going to get myself something to drink because I seem to keep choking on my words. But if anybody needs to find me, you know where to find me. And I would love to hear some feedback. And again, thanks everybody for coming.